Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The first speaker of the afternoon is Vadim Lyubashevsky. He is a researcher at INRIA ENS Paris. He received his PhD at UC San Diego and was a postdoc at Tel Aviv. He works in lattice-based crypto, in particular trying to design crypto primitives that can be used in practice. And he and his colleagues introduced and proved the security of ring SIS, ring LWE assumptions, which have formed the foundations of most efficient lattice-based primitives. Vadim.
Okay, so thank you, Satya. Thank you for inviting me. This is great. Okay, so today I'm going to talk about lattice signature schemes. So, lattices have been pretty popular lately, so one thing that you hear a lot in the introduction of lattice papers is that, lattices you can do anything with them, and you can even be efficient. So it's exciting, efficient. But the thing is, it's true. But those two sets are quite, the intersection of exciting and efficient is almost zero. The exciting things, FHE, multilinear maps. Yeah, that's really exciting stuff. Theoretically, it's amazing. Efficient, not even close. So the efficient stuff comes from the kind of the boring primitives that are like public key encryption, digital signatures. But even that, until recently, it's not been known whether you can actually do even the boring stuff efficiently. Lattices like Alain mentioned some things, but I'm going to disagree with them. Lattices, they gained popularity as a theoretical topic. So there was the great result of ITI about average case to worst case reduction. And for about 10 years, this is what people cited. Like, why do you want to use lattices? Because it has a worst case to average case reduction. Even though really in practice you never do, right? But that was the only thing that we had. So we always cited that, and that's why lattices are important. But it turns out that you actually do things efficiently. So now I don't think we have to lie and say, we're doing things based on average case, worst case reduction, because we really are not, right? We never... That wasn't a question. But I wasn't saying you in particular. But the average case to worst case reduction is really nice because they tell us, these are the hard problems. But then when we actually set the parameters, they're not in the region of what average case to worst case reduction tell us. So to kind of understand how to build efficient things, it's actually important to know how lattice reductions algorithms perform in practice. So that was sort of Damian's talk. And understand what are these average case problems? How hard are the average case problems in reality? And we don't really care about what the worst case problems are. Okay, so this is important to keep in mind for what I'm going to talk about and sort of how improvements come about. So these are not theoretical, these are theoretical improvements, but they're actually also improvements in practice that come from understanding how hard these average case lattice problems are. Okay, so now I'm going to say that all lattice problems are really just the more fancy way of saying knapsack problems. So knapsack problems are very popular in the 80s, bad reputation, so we start saying lattice problems. But it's really just the knapsack problem, okay? So the knapsack problem is the following. You have a matrix, A, right? So this is knapsack over vectors, right? Not over integers, nothing special. So A is random over ZQ. And then there's some small vector in ZQ that you multiply by A. So by small, I mean, let's say small norm. Okay, so not ZQ, but something smaller. And the result is T, mod Q. And the question is, well, given A and T, the blue thing, can you find some S so that AS equals T? It doesn't have to be the same S, right? Because if S has a lot more entropy than T, then there's not a unique S, so you can't really force somebody to find that S, but just find some small s so that AS equals T. So this is it. This is where all the lattice cryptography is really based on, right? It's so it's important to understand the hardness of this knapsack problem. So this is a very sort of unscientific graph. It goes up and down, but it really does look like this. It's important to know that there's some point as you increase the norm of S. So let's kind of take S to be very small, right? If S is very small, then the problem is not hard because, let's say S only has like 2 1s in it, so the norm is small. Well, you can find those 2 1s just by exhaustive search. So over here, the problem is easy. Then it gets harder and harder and harder. Here, actually, the best way to solve it is through lattice reduction, actually the thing that Damian was talking about, how to solve cis using lattice reduction. Then at some point, the problem kind of becomes the hardest. And then it starts getting easier and easier and easier. And if you think about it, if S is, if there's no restriction in the size of S, then the problem is very easy, just by Gaussian elimination, right? So here it's easy, here it's easy, so at some point it's hard. And it's actually hard exactly when the entropy of S is like the same as the entropy of T. So at some point where there's almost exactly one solution, this is where the problem is hardest. So what we want to do, forget about all the worst case, average case reductions, is we want to design a problem that's based on this problem at this point. Right? This is what we try to do in lattice construction. Okay, so now more. If you want to be more theoretical, right? You have these problems called cis, so small integer solution, and that's usually referred to. That's when there's lots of S, so that AS equals T, and if there's lots of S, then in fact there's some S so that AS equals 0, and that's the sort of the standard definition of cis. And on this end is the learning with errors, kind of a really restricted version of a learning with errors, actually a harder version of learning with errors where you don't have many samples. Right? And that's, so it's actually, so I would say that the learning with errors problem is an overkill if we're trying to base it on that, because we almost never have an unlimited number of samples that we have access to solve the problem. So we usually have just a few samples and say, okay, find the S. Okay, so this part is the learning with errors part. Okay, a restricted version. So, right, the cis one is that for all, so the cis version is where, like I said, for all T there exists an S so that AS equals T. So classic cis T equals 0. And so here are some the results that I will talk about, right? So kind of early on, we realized that you could build signature schemes based on the cis problem. And in fact, I should mention that the cis problem is, in theory, harder than the LWE problem. If you can solve cis, you can solve LWE. So it seems like what you want to do is base things on cis. But that's kind of missing the picture of trying to build schemes based on sort of that are hard here, right? We don't really care what the names of the problems are. We want kind of that.
What's the name of the thing in the middle?
What's the name? What's the name? What do you mean? What's the name?
Do you call it LWE or cis or both?
Oh, I mean, this is where like LLE becomes cis, but I don't know. Like at some point, right? They're kind of almost the same problem. The reduction is they're sort of equally hard. So, but the thing is, we can never build anything based on this, so you don't have to worry about it. That has never come up yet. Well, I guess, no. I mean, you would call it cis, right? Because collision-resistant hash functions are really up here. So we call it cis because that's stronger than LWE. But anyway, so we can build signatures based on cis. And they are kind of over here, right? Based on this hardness. But what I'll show you is that really what you want to do is build more efficient signatures based on LWE. And they're kind of on a line over here, and you'll see why this point is going to be higher than this point. I labeled nothing, but you'll see what's going on. And results extend. I'm not going to talk about the ring version of ring cis or ring LWE. I'll just talk about cis and LWE, and everything will extend sort of completely naturally to those two. Okay, so just a review of digital signatures. I don't know if anyone's not a cryptographer here, but let's just do it anyway. So you have the key generation produces a secret key and a public key. To sign a message I, you use the secret key to sign MI and produce the signature SI. And then the verification under the public key of the message and the signature should say yes or no. And hopefully every time you sign a message with the secret key, it verifies with the corresponding public key to yes. And then security is unforgeability. the adversary gets the public key. He gets to ask as many signatures as he wants, and then he has to output a new message signature pair so that it verifies to yes. Okay, so this is the sort of accepted definition of signatures and its security. Okay. So I guess in classical cryptography based on discrete log, RSA, stuff like that, there are two ways to do signatures. And I will only care about random oracle signatures because we're trying to be efficient, so no one in practice, no one really cares that random oracles don't really exist. Okay, so so you have a hash and sign. So this requires a trapdoor function. I guess based on RSA, you have hash and sign signatures. And then there's the Fiat-Shamir transformation, which which gets a signature scheme from an identification scheme, and no trapdoor function is needed. So I will, I mean, most of the talk will be spent here, but I mean, there are some really nice ideas in hash and sign, so I'm going to talk about that as well. I mean, it's sort of a survey, right? So here is hash and sign signatures based on SIS. From GPV 2008, so Gentry, Pikert, by Jonathan in 2008. All right, so let's talk about what a lattice is. All right, so this is all these points. That's Zn, Zm. Okay, the green points, they form the lattice. So here are some green points. Okay, green point, green. I'm not sure how good. Yeah, I think green is a pretty good color here. It doesn't look like any other color on the screen. Okay, so here are the green points, if they form a lattice. Now, all the other points that are not lattice points, they are actually representatives of cosets of Zm mod the lattice, right? So let's define the lattice as, so I'm going to define the lattice as, let's think of it y as a, such that ay equals 0 mod p, right? So all of these are lattice points, and I can find an a so that all these lattice points, when a is multiplied by them, give you 0 mod p. Okay, so let's actually say we start with this, and this is its pictorial representation. Okay, so you can check that it's a lattice because it's an additive group, and that's all you kind of need. All the points y, and all the other colored points, not the green points, they're cosets of Zm mod the lattice. Okay, so the red ones, for example, all the red ones, they're just offsets by the lattice of each other. Okay. So now we know that A times any green vector is 0 mod p. A times any other color vector, let's say yellow, is going to be something else mod p that's not 0. Okay, but it's always going to be the same. Right? A times any yellow point is going to give you the same thing here, right? The same encoding theory syndrome over here. And now there's how GPV sampling works. You have your A, and you have some secret basis T. And this secret basis T has short vectors in it. That's your trapdoor. What you can do is, given A and some syndrome B, you want to find an S so that AS equals B. Right? That's what you want to do. So for any B, this should output a short, so given A and B, it outputs a short S so that AS equals B mod P. Okay, this is what GPV does. I'm not going to explain how it does it, but using a trapdoor basis, it can do it. All right, so now the important properties that we need is that distribution of S only depends on the vectors comprising T. So this is the really crucial part. It doesn't depend on T itself. I mean, it has like lots of vectors. T has some vectors in it, particular vectors. But the distribution of S does not depend on T. It just depends on the length of the vectors in T. Okay, so this is sort of the whole heart of the GPV sampling algorithm, right? It's easy actually to get an S so that A times S equals B when S kind of depends on T. But then that's not good because S is going to be our signature, so you don't want to leak out T. You want S to be independent of T. And so what GPV sampling does is the following. So there you have some syndrome B. It's going to find some coset representative, so A times this equals B. But this is actually easy to do if there is no restriction on it being short. You just use Gaussian elimination, you find some red vector so that A times red equals this coset. So let's pretend it's this one. Okay, let's say we found this one very easily, no problem. So what GPV actually does is then, given this, it's going to find a lattice vector that is pretty close to it, but doesn't have to be the closest one, but somewhat close to this, this vector here. Now, by translation, you can just sort of translate it to make this lattice vector the origin, right? Because this is just a lattice vector, we can get it to be the origin, okay? And then this turns out to be a somewhat short vector, right? Because this was our original vector, this was a lattice point close to it, we translated it down, we did this sort of parallel. So this is now a short vector. And A times this minus a lattice vector, which is short, equals this, because A times green is 0. Okay? So this is how so GPV, I mean, the hard part is, given this, find the short vector here, right? But once GPV does that, we can find the short S so that AS equals B. Okay? So what are the properties that are needed for S? Well, like I said before, distribution of S only depends on the length of the vectors comprising T. We'll see why in the proof. And the following should produce the same distributions of SB. So there are two ways. So one way is to look forward. One way is going to be how the signature is actually produced. And the other way is how the proof is going to do it in the simulation. And you want those two distributions to be the same for the security. Okay? So the following should produce the same distribution of S and B. The first thing is the honest way, is you choose well, not the honest way, actually this is the dishonest way, is you choose an S according to some distribution, and then set B equal to AS. Okay, so this is sort of the obvious thing, right? You pick an S, A times S equals B, that's it. The second way that should produce the same distribution of S and B is to choose a random B first, then run GPV, use T, to find an S so that AS equals B. And so given those two distributions, either come from A and B, you should not be able to figure out where it came from, okay? So this is what they have. And so this first property is guaranteed by the GPV algorithm. And the second property is true if S has a large enough entropy to make AS equals B uniform mod P. Okay? So when S has big enough entropy, A times S will be uniform. All right, so now here's the hash and sign lattice signature. Your public key is going to be A, this matrix A. You can think of it kind of making a lattice, in the way I described before. And then your secret key is going to be this basis, the short basis for the lattice. So the public key is A, secret key is T. To sign a message M, the first thing you do is you construct B by applying the random oracle H, which is a random function, to M. So now you get B equals H of M. You use the GPV algorithm to find the short S, that AS equals B. And then S is the signature of M. That's it. It's actually quite simple and elegant. And then the verification just sort of does the obvious. It checks that S is short and that AS equals H of M. All right, and here's how the security proof works. Let's say we're given an A, and we want to solve the sys problem, meaning we want to find a small vector, I don't know, call it Z, so that AZ equals 0. Well, we obviously do not know short vectors in the lattice formed by A, right? So when the adversary asks us to sign a message, so we give A as the public key to the adversary. So when the adversary asks us to sign a message, we obviously cannot do it, honestly. So we have to play a random oracle tricks. What we do is we say, okay, we pick the signature. So we say, okay, this red thing, that's going to be the signature from the distribution D. Then compute A times S. It's going to equal to something. And we say, oh, that's H of Mi. Right? So then we program the random oracle to say this is H of Mi. I mean, this is how all the hash and sign proofs work, right? Okay, and then we give the signature and the output of the random oracle and the output of the H of Mi to the adversary, and he says, well, yeah, okay, that's correct, I guess. Okay, so sometimes the adversary may also ask you for a random oracle query, no problem. We can give him a random oracle query. We just choose an MJ. We just pick a random element, say that's H of MJ. But but that wouldn't be good because things will go wrong. So we actually want to, every time he asks for a random oracle query, we actually do want to pretend he's asking for a signature. So we also come up with a signature if he were, we don't have to give it to him, but we come up with it just in case. Okay. So now at some point the adversary is ready, so he's ready to forge. So he says, I will forge a signature of M. We say, great. To forge on M, though, the adversary needs H of M, right? I mean, because he's going to come up with an S that AS equals H of M. Well, how does he know H of M? He has to have asked it of us. So at some point, he must have queried the random oracle on M and asked us for H of M. Okay, so M is one of the MJ. He asked for H of MJ. Well, therefore, by the way we did things, we actually know an SJ so that ASJ equals H of MJ. So here is our SJ that we chose a while ago. So we have ASJ equals H of MJ. And now here is the new signature that the random oracle that the adversary forged. But they're equivalent. A times our thing equals A times his thing. Okay? Therefore, the difference of these two things multiplied by A is 0. And that's the solution to cis. So these are both short and hopefully non-zero. And the reason it's not 0 is that it's this entropy argument again. For random B, there is more than one likely possible output. So it's actually statistically impossible for the adversary to know which S we knew, right? Because there's lots of possible S for a given B, so that's it. Okay, so there's nothing really here. Okay, so that was hash and sign signatures. Okay, so if there's questions about that, I can answer some. If not, we move on to Fiat Shamir.
Full domain hash argument essentially.
Yeah, this is exactly the full domain hash.
So all these tricks of improving the rejection tightness, all those apply there?
So you're asking about the reduction tightness, about not caring about the query. So I'm saying this is already tight. So here's, this question always comes up, and I'm happy that I can finally answer it. So you're thinking of for example, the RSA things, right? Where you have to guess on which message he's going to query, right? So the reason you had to do that is because there was no hash function. This RSA function, the equivalent of A times S, was injective. Right? There were no two S's so that A times S, or no X's so that G times X1 equals G times X2. G to the X1 equals G to the X2. Right? Here, on the other hand, we're choosing it so that it's not injective. It's actually quite lots of collisions happen. And for this reason, we never have to guess which thing. And actually, so if you know the way that the only trick I know, I think it's Katz Wong maybe, that kind of makes it more tight, is they did exactly this idea of introducing collisions into the RSA signature, right? So, but here that's already our problem. That's already our hard problem. Cis is, so it's okay. So there's no problem with okay, that's a good question. Okay, so let's move on. Okay, so now we're going to do Fiat Shamir. All right, so here's the main idea. And if you know Schnorr signatures, think of Schnorr signatures a little bit, but there's going to be a major difference, but we won't get to it yet. Okay, so the secret key is going to be a matrix S, and the public key is going to be a matrix A and a matrix T, which equals to AS. To sign a message mu, so Fiat Shamir comes from transformations from ID schemes, but I'm not going to show the ID scheme, but it should be sort of implicit. Okay, so you pick a random Y, compute the challenge equals H of AY mod Q, and the message, and then output a possible signature Z equals SC plus Y. So everything in orange represents elements that are small, and everything in black elements that are big, right? So don't worry about what small and big means, but just it's small enough so that like small multiplied by small is still small. So if there's a small vector matrix multiplied by a small vector, it's still the result is going to be a vector with small enough coefficients. Okay, so small times small is small. All right, so this is the signature that we would try to do if we just did straight Schnorr. You know, we take Schnorr.
If H is a random marker, why do you need a random line?
Sorry, what?
Do C equals H of AY mod Q. Why not apply just to the message that you get a random string?
Sorry, what?
C should be a random string independent of the secret. C equals H of AY mod Q, where Y is random.
Yeah.
So randomize the signatures, right?
Yeah.
It makes this deterministic by not just applying H to the message.
What do you mean I'm making? No, I'm not making deterministic. This comes from identification scheme where so there's 3 steps, right? Commit, challenge, response, right? So the commit is AY, the challenge is C, the response is Z, right? But if it's a signature scheme, I'm playing it with myself, so you have to kind of trust me that the commitment is random. Oh, sorry, the challenge is random.
So you commit to the challenge.
So the challenge is a function of the commitment because the challenge has to come after the commitment.
Yes. Okay. Would it work if the challenge depends only on the message?
No, then it's false. Then it's not secure. Because if the challenge depends only on the message, I can just compute the challenge for any message and then go backwards and figure out what the okay. So and the output is ZC. Okay, this is what we want to do, but this doesn't quite work. So verification, but it's something close to it will. So here's the verification of ZC. Check that Z is small, and that C equals H of AZ minus TC mod Q. Again, if you know Schnorr, you can probably sort of map things to exactly this. Okay? So why does this work? Well, because AZ is TC plus AY. It's minus TC just leaves you AY here. Okay? So this verifies correctly. And the reason that Z is small is because small times small is small. All right. So here are the 2 things that we want. And that we had in Schnorr. Is that given the public key, the secret key is not unique. Well, we actually did not have that in Schnorr. And we don't need it here, but for the proof, let's just pretend we will. Maybe think of it as Okamoto. Think of it as Okamoto scheme. Maybe that's a better analogy for this. Okay, and then think Okamoto is definitely a better analogy here. Okay, and then the output is ZC, and what you want is the signature to be independent of the secret key. Okay, so these are the 2 properties that we want, which is kind of the same thing we wanted in the hash and sign. We wanted the public key, the secret key is not unique, and you want the signature to be independent of the secret key. So these 2 things we always kind of want, no matter what you do. And here's the security reduction in case that holds. Okay, so we get our challenge is A. We have to find the short vector so that A times this vector is 0. Our simulator picks a random S, gives A and AS to the adversary as the public key. The adversary asks for signatures of messages. The simulator actually knows the secret key, so he can give signatures of messages, no problem. At the end, the adversary forges on mu, gives ZC. Then, if you know the forking lemma, we get him to produce Z prime and C prime for the same message mu. If you don't know the forking lemma, think of rewinding. If you don't know rewinding, well, just think of, I don't know. Think of the previous thing we did. It's not related to this, but I mean, if you understood that, that's better than not understanding it. I don't know. No, I don't know. So sorry. At this point, you kind of, it would be, yeah. Okay. So let's pretend we all know about forking lemma or rewinding. If you know both, then think of forking lemma. And okay. So Now what you get, if you have two different signatures for the same message, is that you get that A times Z minus Z prime plus T times C prime minus C equals 0. It's just because the two random oracle queries have to have the same input into them. Okay? And the input was exactly this, so, okay, and then you just, since you know that T equals AS, you get A times this equals 0, and you hope that this guy is not 0. Right? If this is not 0, then cis is solved. And so for this thing in the middle to not be 0, it's important that the adversary does not know S. Because if he kind of knows S, then he can actually do the honest signature. You know, these signatures could be the honest signature, and then obviously it's going to be S. It's going to be 0. Right? If he signs this using S the way you signed it, then this is going to be 0. Right? If it weren't, then you could solve cis yourself. Right? If you could just sign with the honest S yourself and somehow get a collision, you'd be done. Okay?
Can you try to give the intuition of why it would take to rewind the I mean, or why would you get two different signatures?
So you're asking me what is the forking lemma and why does it work?
Yeah. I mean, very short.
So the idea is the following. Do you know rewinding?
Yeah.
Okay. So we can work with that. So in the rewinding, right? You have the challenge, right? And we rewind the adversary to answer the same challenge twice. Okay. The only difference with signatures, right, is that you can you give them outputs of the random. So you give them outputs of the random oracle, right? And you know that these outputs of the random oracle kind of serve as the challenge. Okay, except, so at some point you change the output. But the only difference is that you don't, in signatures, in identification schemes, when you do this rewinding, the adversary has to reply to those challenges because he's in the stage of the security reduction where he has to reply to the challenge. Whereas in signatures, right, you have no idea what he's doing, right? He might just, out of curiosity, query something. You have no idea when he's going to forge. So that's the forking lemma kind of says, well, you guess which of these is going to be the important one. Then you change it, and then you change everything afterwards as well. And if that really was the important one, he has the probability, instead of forging with probability epsilon, it's epsilon squared. Okay? Is that? Okay. All right.
So here you have that tightness gap, right?
Yeah. Here you do have the tightness gap. Yeah. Okay. So the security reduction is right. Basically, from this you get a solution to cis. And what we want, in order to get this reduction, we needed two things, right? We needed the signature ZC to be independent of S, so that this thing is not 0. This thing in the middle is not 0. And for this to be small, right? Because if this is not small, then the signature verification fails as well. All right, so now I'm going to sort of make an important interlude that's kind of really at the heart of, even though it's really simple, but it's really at the heart of improving this, the efficiency of all these signatures. Okay, so instead of basing schemes on cis, why do you want to base it on LWE? Okay, so the things I said is the following. You want, given the public key, the secret key is not unique, and the signature is independent of the secret key. Okay, but what if, given the public key, it's just computationally indistinguishable where the secret key is unique? This would be okay too. You use the hybrid argument, maybe just be careful. It should work. Okay, but why would you want to do this, right? I mean, the proof can be modified to work, but why? The question, why would we want to do this? And here's the answer is in this graph, right? So notice here, when we had z equals s times c plus y, even though z is small, it's still a little bit bigger, right? It's because you multiply s by c. So the size of z is bigger than the size of s. Okay? So the hardness of solving cis is, if you saw in the proof, it was like our the vector we found was somehow related to z. It was z minus z prime plus something, okay? So the norm of z is really important to the hardness of cis. The bigger z is, the easier the problem is. So we want to keep z small. On the other hand, you also had this s. And when I said, given the public key, the secret key is not unique, S must also be in the region where there's lots of possible S's so that AS equals T. So S is also in the cis region. So here's what it looks like if we just think about what the hardness of finding S is and what the forging signatures, right? So here was S. We just needed S to have, just force a collision, just one collision. So S could be, as close to this point as you want. Okay? But now the hardness of forging signatures was not really finding S. It was finding something on the order of Z. And Z was bigger than S by a gap of about root n. More or less. Well, we'll need it to be more, but root n, but it's because of something else that comes later. But anyway, there's a gap. Okay? But now, since there's a gap, we move down on the hardness of solving cis. Okay? So the idea is the following. Well, why not move the secret key over here? You still have this gap, and then the hardness of forging signatures is on the same level as the secret key. So, but the secret key is now based on this problem on the other side of the graph, which is LWE, whereas cis is still, forging signatures is still cis. So, and this actually saves a lot. Okay? So this is why we want to have a secret key based on LWE rather than cis. Okay? That's why we don't want this many secret keys for the same public key thing. This is, this is what you want to do, right? Because exactly, it's the minimum. If you go over too much, then okay, yeah, forging signatures will be really hard. Just by looking for Z will be really hard, but that's silly. You should just look for the secret key. This is the best practical. So you wanna actually figure out what these graphs are, right? And then put your secret key in this, so they're at the same level. Okay. So all right. So now the signature scheme. Okay, let's go back to the signature scheme. So this is why we don't want S to be too big. All right. So now how do we pick a random Y? Right? Can we make Y uniformly random mod Q? No, right? Because then Z equals SC plus Y, then Z will be too big, and cis and forging will be easy. So you can't have Y uniformly random mod Q. Okay, because the size of Z depends on Y. Okay. Can you make Y small? Well, if this works, then Y should be small, but can you just make it small and that's it? Well, no, because then in this case, Z will not be independent of S. Because when you output SC plus Y, if Y is not too big, just think of coefficients of Y not being too big, then SC plus Y may leak something about S and C, right? If let's say just say Y is like 0, 1 coefficients, then if you know if you get something Z that's too big, that's sort of the maximum it could possibly be, it tells you something about the coefficients of SC. So that's not good either. So what you want to do is rejection sampling. Okay? So you want to keep Y small, but output ZC only if Z meets certain criteria. Otherwise, repeat. And just do this a few times, pick a random Y, do this. If it doesn't work, okay, try again. You don't want to try too many times. But if it outputs something, okay, you're done. All right, so here's what rejection sampling is. Let's say you have access to some samples from G of X. This is a distribution. For some reason, this is all you can sample. But you don't want it. You want f of x. Okay, you want this distribution. So how do you get this red distribution if you only have access to the green distribution? Okay, I don't know who was the first person to ever come up with it. If you ask somebody, they say it's that person from their nationality. So they just go back a few centuries and say it's. So I don't know who did this, but anyway. So the idea is you sample from G of X, but you only accept X with probability f of X divided by m times G of X, where m is some constant, so that f of X divided by mg of X is always less than or equal to 1. Okay, because otherwise it doesn't make sense to accept with probability if it's more than 1. Okay? So, and you can see that this is sort of obviously gets you the right thing, right? Because what's the probability of getting X? It's G of X, so the probability you actually selected X, times the probability that you will actually output it, which is f of X divided by mg of X, which is just f of X over m. So the probability of you outputting, given that you output something, its distribution is going to be exactly f of x. There's this divided by m, but m is a constant. So all it controls is what's the probability of rejection, right? So you'll actually output something with probability 1 over m. So the expected number of times you need to do this rejection sampling is m. Okay, so you don't want m to be too big. All right, so something is output with probability 1 over m. So the nice thing here is that, well, let's say you don't have access to g of x, you have access to h of x, but you still want to get f of x, no problem, right? As long as f of x divided by m, for some m, fits underneath both of them, it's okay. Rejection sampling will work, no matter if you start with g of x or h of x, and nobody can actually figure out which one you started with first, g of x or h of x. Right, so this is rejection sampling. It's impossible to tell whether g of x of h of x was the original distribution, which means that the original distribution remains hidden. Okay? And the original distribution, if you go think about what we're doing, is that original distribution is what depends on our secret keys. The secret key stays hidden. As long as the original distribution is always above f of x divided by m. All right. So here's the idea. You take so these are really terrible Gaussians, but they're Gaussians. Okay? You pick a random y, but you pick a y from this distribution, from some Gaussian distribution, or whatever it is. Now, y plus sc is just a shift of y in the direction of sc, right? So this thing, this green thing, is the distribution that we end up with, but we want to hide it because it reveals sc. Well, so the distribution we want for z, I mean, we can choose any distribution, but it turns out the good one to choose is actually the distribution of the original distribution of y. Okay? So you want to end up outputting this red distribution, but you have access to either this green distribution, this purple distribution, or really anything that's an offset of this red distribution. Okay? So yeah, maybe I'll skip the sort of more mathematical things. The normal distribution. I mean, actually, honestly, I don't really know why it's the most useful thing here. But it turns out the normal distribution gives us really the best way to do rejection sampling. Well, some way of using the normal distribution. It's just, you want two distributions that when you shift one, they kind of gives you back what you had before. And the normal distribution seems to give you the tightest thing. So, okay, so here's the normal distribution, whatever it is, it doesn't matter. It's centered at 0, standard deviation sigma. Here's an example. Okay, here's one normal distribution, here's another one with a bigger standard deviation. Then they can be shifted, right? So by shifting, you just subtract in the exponent. Then n-dimensional normal distributions are exactly the same thing as one-dimensional, except now you're dealing with norms of vectors in the exponent rather than just integers. Okay, so here's a two-dimensional example of a normal distribution. Okay, what you expect. So then there's the discrete normal, right? Which is, so what I showed before was continuous, but here we only care about discrete normals, meaning I want the distribution to be centered on integers, on Zn. So, I mean, that's also, I mean, you can define that, right? By just, the distribution will be defined, probability of x is the normal distribution of x, evaluated x, divided by the sum of all the, I mean, just to normalize, you have to divide it by the sum of all the integers. The normal distribution evaluated all the integers. I mean, nothing, just normalizing. Okay, so now here's rejection sampling. Right, you want to figure out what is the maximum value of s times c, because that will give you what is the biggest shift, right? Because the bigger the shift is, the harder it is to fit your original distribution underneath the old one, right? The bigger the shift is, the more they're going to look different. The more different they look, the harder rejection sampling is to do. Okay, so, right, so then you take your red one and you shrink it by some factor m to fit underneath both of these. The problem is, with Gaussians, they will never fit, right? Because at the tails, the ratio is going to actually kind of, the ratio increases at the tails. And so it's going to be, for any m, this green one is always going to be below the red one over here. And this is bad, but that's okay. These are events that will happen with very little probability. You will, with very small chance, will you actually pick something that's over here. So it's no problem. I mean, you have to kind of be careful, right? You have to make sure to pick an M so that for points that are really far away, that it only doesn't work for points really far away. So okay, but we can do that. So what turns out that if sigma, the standard deviation of our, the Gaussian that we pick the y from and that we want the z to be from is bigger than 12 times this maximum, then we're only going to have to repeat things with about e times, so 2.7 times. Okay? So if it's 12 times bigger, the red thing fits under any shift. Okay? And this 12 comes from the fact that it's very unlikely to get something within 12 standard deviations of a Gaussian. Okay, so now, I mean, there's this 12, right? I mean, the 12, again, comes from the fact that we want all but the very, very, very distant points to fit underneath. But you still have to multiply by this 12 to make sure that the points that are far away but not that far away fit, right? And the problem is with the tails. So this is where sort of the math thing comes in, right? We want to try to improve rejection sampling. 12 is what if you want 2 to the minus 100 statistical distance, then you choose 12, right? I mean, yeah, I mean, if you want to, 2 to the minus 100 is not enough, well, you choose, 14. Right. But if it's like log n, if you want to do asymptotic, log n, you will be within 2 to the minus log squared. Okay? So 12 is something to get 100. Okay? So here's the idea for improving it, right? And this is from the recent result. I mean, don't worry about this. Let's just look at pictures. Here's the rejection sampling that I just talked about with the Gaussians, right? You have, because you have to divide by such a sort of, because a shift happens and you have to divide by, something that's fairly big to get them to fit, to get the kind of the tails to fit underneath for all but the very extreme points, you're dividing by a lot, and the two distributions, here is the distribution you're sampling from, the blue one, right? This is on 2 scales, right? What you did is you shifted this guy over by this, so projecting onto this axis, it's still a perfect Gaussian. Projecting on this axis, it's a shifted Gaussian. But you have to fit this red thing underneath both, because that's what fitting it underneath a Gaussian means. So you have to, the two distributions don't look very close to each other. So the idea, and the problem is again the tail. So the idea is, what if you add another Gaussian? What if the distribution you're sampling from is a Gaussian on both sides, right? So it's a shift in both directions. So rather than having just one shift, you somehow end up with 2 shifts. Right? So then it's great. At least the problem is kind of solved, because at the tails, I mean, the blue one will always be bigger than the red one if you divide by something, because this is a shifted Gaussian, so it's bigger here. This is a shifted Gaussian here, so it's bigger there. Right? So they kind of take care of it. And so the 2 questions are, all right, so this is great, but how do you do it? Okay, so getting this bimodal Gaussian, that's easy in the signature scheme. So let's look at the previous thing. Here, z was s times c plus y. So it was a Gaussian y shifted by sc. But what if you want a Gaussian that's shifted by sc and minus sc? Well, instead of adding sc, first you pick a random b in negative either 1 or negative 1 with probability 50%, and then add to y b times sc. So now, what do you end up with? Well, with 50% chance you're here, and with 50% chance you're here, right? So, okay, so that kind of handles that. Okay, so it's easy to get a distribution, but does the scheme still verify correctly, right? You can't just pick any distribution. I mean, you can pick any distribution you want, but at the end, the scheme has to work. So But first, why is this nice? So just to show what the nice thing is, the standard deviation now goes down by a lot. Before, the standard deviation for the same E, you had to have standard deviation be max of SC times 12, whereas now it's max of SC divided by square root of 2. So almost like a factor of 20 improvement. Or sort of asymptotically, it's a logarithmic factor in the standard deviation, which leads to significant savings. And the verification, now how does the verification work? Well, the verification checked that h of az minus tc mod q, comma mu, evaluated to c when applied to the random oracle. But this doesn't quite, I mean, before it worked out great because b times tc minus tc plus ay was ay. So this part was just ay because b was 1. So previously, pick a random b in 1, but now it's in 1, negative 1. So what you need to happen is that tc equals minus tc, right? You need the two things to cancel out no matter what. You want this to be periodic mod 2, and you can do this by picking an s so that a times s equals qi mod 2q. So now, this is our t now, qi, and you notice that this t equals minus t because we're working modulo 2q. Okay? And you can prove this is still secure. And now to sign, we do what we previously did. We compute this, pick a y, compute c, choose a random b, and then output z equals bc plus y, and do rejection sampling with the bimodal distribution. And verification is exactly the same, checks that it's exactly the same. Okay, and the security reduction works in a similar way. You have your A, you pass it to the adversary, he gives you a mu-I, you pick zi-ci from the correct distribution. You can do this, you can program the random oracle. In the previous scheme I didn't, here I do, it doesn't matter really. You pick it from the correct distribution because we know what this distribution is and it is not dependent on the secret key. Okay, we program C equals this, and then we send the signature to the adversary until he sends us two different messages, which we get using the forking lemma, and then we get a times z minus z prime equals 0 mod q. Okay. So I went fast, but there's nothing too different in the security proof than before. Okay, so this is the basic idea. So the main sort of theoretical idea was to figure out how to do the rejection sampling optimally, right? And so the optimal way that we have right now is to do rejection sampling is to have this bimodal Gaussian that kind of takes care of the tails on both sides. Is there something better? I mean, I don't know. I mean, it wouldn't surprise me, but right now I have no idea, so it's a nice open problem. So the optimizations that we had is, base the problem on the hardness of the NTRU problem, not cis. So, so instead of, so the NTRU problem, when I say the NTRU problem, I mean you take two small polynomials in some ring, divide them together, the result looks random. Okay, is it true? I don't know, but we haven't been able, I mean, for 15 years, this is what people believe. Okay. So then you can also compress the signature. So you can notice not all of the signature needs to be output. Doesn't matter. A few other small tricks. And so I don't know if you can see it. Yeah, I guess it's okay. So let's say you want 128-bit security based on what we currently know as the best lattice attacks. I mean, what Damian was talking about. Well, if you want 128-bit security, you can get signature size to be 5,000 bits, for example. Right, so the equivalent thing for RSA maybe is, I don't know, 4,000 bits. So it's a little bit bigger. The secret key is a little bit smaller, but okay. I mean, same thing. Signing is much faster. A big order of magnitude. And verifications are much faster as well. So when compared to RSA, it's, except for signature size, which is maybe 1,000 bits longer, everything else is much better. I mean, the one disadvantage of RSA, I would say, is that, I mean, all these rejection sampling and Gaussian sampling, they're not super easy to do in, for example, in a smart card, but people are working on algorithms to improve on that. I mean, but I guess, if you want to do RSA properly, I mean, you don't just, I would just square and multiply, but that's probably not the way they do it, right? So maybe it's not very trivial the way they exponentiate either. So I don't know. I mean, if you're trying to optimize everything, maybe RSA is not that simple. I don't know. But yeah, sort of we get something that's fairly competitive, and I would say that encryption and signatures are so far the only two things that we know how to do really well from lattices. Yeah, I mean, maybe the same ideas can be. I mean, the same ideas from this rejection sampling are also used in the identification. So if you want to do zero knowledge proofs, it's the same idea. So the rejection sampling can be useful there. But so far, these techniques have not improved upon the more complicated. I mean, these ideas haven't all of a sudden made FHE to be super efficient or multilinear maps. But progress is sort of slow. I mean, this is about 1,000 times better than what we had about 5 or 10 years ago. So it's all right. Okay, so this is all I wanted to say. Thank you. Yeah. Well, okay.
I have a question. Isn't the rejection sampling inherently prone to timing attacks? Because you can learn the distribution.
Well, the thing is, what is the attack that you're thinking of, timing attack? Because the thing is that
if you know how much repetition it took to generate a signature, and you might learn M, and then you can.
Well, M is public. M, everyone knows M.
But okay.
So I will tell you this. I mean, there might be attacks, and I mean, there might be even easy attacks, but the obvious thing of maybe what you're thinking of, depending on the secret key, you might reject more or less. That's not true. For every secret key, you reject exactly the same way. Whether or not you reject may tell you something about why. And that, I don't know. So if you're... But I think once you start looking inside the scheme itself, if you're able to probe inside and get some values, there might be an easier way to do it than just by looking at the rejects. But if all you're doing is you figure out whether or not I'm rejecting or not, you learn nothing. Because for every key, I'm rejecting with the exact same probability.
Is there any specific use case defined to adopt the lattice digital signature? So far, in industry, most of the applications, use cases, or semiconductor companies, all are deploying the traditional digital signature scheme. So, any specific use case can you propose?
Okay, one thing you could say is, okay, if quantum computers get built, you want digital signatures based on lattices. Okay, so that's one thing. But let's say before quantum computers get built, let's say you don't believe that quantum computers will ever get built. Because I would argue that if you know they will be built in 10 years, signatures that are made now will be completely invalid in 10 years. Right? So if you want things that are signed now to be valid when quantum computers get built, you can't use something classical. Right? Because then they can just be forged retroactively. Okay, so that's one thing. The other thing is, okay, if you care about verification time, so all lattice-based signatures have very fast verification time. It's just a vector matrix multiplication. So that's another one. And a third one actually somewhat deals with the leakage resilience thing. The fact that lattice signatures lattice operations just sort of linear, it's much easier to mask them. So there was some work done in a different direction, but using kind of the same idea that the more linear you have, the more linear a function is, the more easier it is to kind of achieve higher orders of masking. Because then the reconstruction is just, you do something many times, and then you just add out up together. add it back up together, and that gives you the correct result. Whereas if something is non-algebraic, but maybe with the discrete log you can do something fairly similar. So maybe your leakage resilience is not the best thing to compare it to RSA. I don't know, but I mean at this point I would say it's the conjectured security against quantum computers and the fast verification time. I mean, will I tell you to stop using elliptic curves and switch to lattices? No. I mean, at this point, right? I don't think we're there yet. I mean, I certainly wouldn't use anything based on lattices, right? At this point, but the point is, we're getting there, and hopefully there'll be much more cryptanalysis, and then we'll be able to get to the point where lattices will give you a good alternative. So there's a
just addition to that, good question.
Yeah.
So recently NTRU has been actually licensed as an open source
NTRU encryption.
Encryption, not the signature, the encryption.
Okay.
So maybe there is some reason behind that.
Right. Okay. So I guess it's some rumor. I don't know much about NTRU, but like Sony used NTRU encryption because it was faster.
Yes, even I heard that.
Yeah. Okay. So okay.
I don't know that.
This must be true then. Yeah. 2 people heard it. Maybe you told me. It still counts. Okay. Just synthesizing. Yeah, Tanya.
So now I have 3 comments. So one
Wow.
was, how sure are you about your security levels there?
I mean, this is based on the best known attacks. We took a margin of error, of course. I mean, I would say, even breaking this toy example here, I don't know if one can do it. Even though we conjectured to have less than 60 bits of security. I mean, all of these, I think we really took some really worst case things, worst case assumptions on how the algorithm behaves. I mean, best case assumption for the algorithm, worst case for us. And we kind of came up with these numbers. So based on what's currently known, I would say, yeah, this is fine. Can something come up tomorrow, the better? I mean, that's not...
Okay.
Like I said, I would not use this, but until more cryptanalysis is
I'm more
done.
asking as a cryptanalyst, like, would you accept a break which shows like 40-bit security for the top one? Not that I have one.
Well, if you have 40-bit security, then you should be able to
then it's still
actually
less
do
than
it,
60,
right?
But, yeah, okay.
No, but if you have 40 bits but you can't do it, then I question your 40 bits, right?
Second one, how does it compare to hash-based signatures?
So in hash-based signatures, the secret key is much bigger. I mean, I would say it's about, what, 30, maybe 30,000 bits?
If you accept that you have a pseudo-Raman function behind it, it's not so bad, actually. Then you can keep AES as a background.
But how do you keep generating a new secret key without storing?
You have to do it once, but you can forget about them.
But you have to store something along the tree, right?
No, you can recompute most of those.
Okay. Oh, okay, I see. So you're saying you just take a random oracle. I mean, as your one-time signature, right? You take so how many bits?
You take a hash function you're very comfortable with, say,
okay.
SHA-256, where we have more good feelings about security.
Okay. So the signature size would be what, about 128 squared? Right? So if you base it on SHA, right? So you you sign every bit. So you have 128.
Okay, you're thinking about Lampert. So if you do internet, so short answer, you're getting actually into the range where hash functions is also very, very efficient. They can beat RSA right now.
So what are the what are the parameters?
So with SHA-256, they get 128-bit security. I don't have the numbers right now. There's a paper by Andy
Holsing.
Yeah. Good. Can take this offline. Last thing was because Praveen mentioned NTRU, so there is also an NTRU signed version out very recently.
Yeah, I saw that. Well, okay. So what they do is, I'm being taped. What they do. So it's very much based on this idea of rejection sampling, but they introduce it. So instead of using the NTRU problem, a bit ironic, they use a different assumption, which I don't know. I mean, I heard Jeff give the talk, and the way I understood it was sort of for historical reasons. He wanted that assumption back in the 90s, but they couldn't quite get it to work. But then with rejection sampling, they figured out how to get it to work. As far as is there any advantage of that over this? I mean, the numbers, just based on the signature size and stuff, I don't see it. But there might be some other uses for that thing. Although right now I don't quite see the advantage of doing what they're doing. If you see an advantage, I would be very curious to know what it is. So, I mean, their assumption is basically instead of this matrix A that I have, is that it's a fixed matrix that's a submatrix of the FFT transform. So whenever you compute A times S, it's actually evaluating S. It's the FFT coefficients of S on on some hopefully random subset of S. And the idea is that if you know the complete FFT evaluation of something, then you obviously have something. But if you only have, let's say, half of the FFT evaluation of some short vector, you cannot find a short vector based on just half of its FFT evaluations. That's something you need to assume is hard, although I'm not sure that the end result, you get actually a proof of security based on that. But that's the minimum you need. That's sort of all yeah, Dominique?
So you gave us the main current motivation for lattice-based crypto, the quantum computer, or as one very important one. But
yet there's rewinding, yeah?
Sorry?
And yet there's rewinding.
Exactly. So
okay.
Have you checked how these signatures work with what we currently know about quantum rewinding? So the first one seems to work with generous result, but you will not be able to use this tightness trick, I think.
Yeah. Okay.
I'm not totally sure because I couldn't follow all details there, but
okay.
But the second one I think is probably unknown, right?
Right. So as far as I know, it's not known. So one thing we can do is we can set the parameters in a certain way that rewinding is actually not necessary. And it's based on kind of the same idea as if somebody knows, so I already mentioned the Katz-Wang paper, but that paper also had another part, which is a DDH-based scheme that does not use rewinding. So basically you have like a Schnorr-type signature, but it's based on, instead of being based on discrete log, it's based only on DDH, and there's no rewinding at all. So it's completely tight. So we have there's a version of this based on lattices as well. It just comes from setting parameters a little differently. But the problem is you set parameters a little differently and it becomes less efficient. You're kind of more down on this scale. So, but the fact that all you have to do is change parameters makes us a little confident that whatever rewinding, whatever quantum algorithm can.
It means it still uses random oracle.
It still uses the random, but it's okay. But
then it could be still tricky.
No. I think that case was actually analyzed in some Asia Crypt 2000 by Fishlin.
2013?
No, not 2013. Maybe 2000.
I think there is a paper on Fiat Shamir.
It's in every Asia Crypt. There's one in
by Fishlin.
It's in no. I think it was the original one was maybe 2010, 2000. I don't know. It appeared early. It was on ePrint for a while. I think they actually analyzed by Christian Schaffner. He was on that paper too. I think they analyzed it and they said, yeah, it's okay. If I wouldn't bet to anything on it, but there's no rewinding, and the random oracle is used in a pretty safe way, the way that they were okay with. So that one is secure. So this one, I don't know, but it would be very strange that for a different set of parameters, all of a sudden this becomes yeah, I know. This becomes insecure. I mean, this would be really, really, really interesting, actually, if this actually does happen. Because, honestly, I don't see how it could possibly become insecure for a harder set of parameters. Yeah, but yeah, sure. This is definitely an interesting open problem, which I don't know the answer. But yeah, this is definitely one of these things that is a bit annoying, that you have rewinding based on against quantum. Yeah, it's a good question. Yeah.
The first scheme you mentioned, you didn't use any Gaussian distribution or Bimodal Gaussian, and then you change it to.
The first scheme, you mean?
The first one that uses the same equation AY plus.
Yeah. No, it was insecure.
You told that we can choose a rejection method to prove that this is secure.
Oh, okay, yeah. Choose any function you want. Just make sure the rejection sampling works. All right. So maybe you cannot use the uniform distribution over a finite range, and that works as well. But the Gaussian one is tighter.
My question is that when you introduced bimodal Gaussians, what was the main improvement?
The standard deviation you need for the Gaussian shrank by a factor of 20.
A smaller standard deviation, so we can
so the signatures are smaller, and then
parameters.
the dimensions can be smaller. Yeah.